Let's continue talking about linear motion. Let's talk about equations though. So calculus, equations for motion. And we're also going to talk about what is called the kinematic equations. On the test notes, this is also written as the big three. So in previous videos, we've already mentioned the average velocity being the change in position in some period of time, average acceleration being a change in velocity in some period of time. But oftentimes we don't want to know just the average value. We want to know the value at an instant. So again, as we talk about that, either one of these, we're talking about having the limit. So still talking about a delta S over delta T, where the limit of delta T goes to 0. What that leads us to is we can find instantaneous velocity, or at least the equation that describes it, by differentiating, taking the derivative of the position function as a function of time. Similarly, we can find the equation that describes the acceleration at an instant in time by taking the derivative of the velocity function with respect to time. Now, of course, to actually take the derivative, we need a function. So we would need a function describing the position as a function of time. So position as a function of time, we would have to have something that depends upon time, like 4t squared or something like that. This is just an example. If that is our position function, taking the derivative, we would end up with 8t. So this would be the equation describing the velocity as a function of time. What we mean by that is time is in here. We'll get a different position value when we plug in a different time value. Similarly, we'll get a different velocity value when we plug in a different time value. If we take the derivative of this velocity function, we actually just get 8, meaning this acceleration is constant. Acceleration does not need to be constant. We could totally, another example, we could have a position function that was, say, 3t cubed. So just another example. If we take the first derivative, 3 times 3 will end up with 9t squared as our velocity. We take the derivative again, we'll get 18t. This represents that the acceleration is also changing with time. Ultimately, all that means is that the velocity is not going to increase or decrease at a constant rate. It's going to increase or decrease at a changing rate, which is fine. The other thing, so this we've mentioned before, finding velocity by taking the derivative of position with respect to time, finding acceleration by taking the derivative of the velocity with respect to time. But hopefully you should have learned that we can also do the antiderivative, the opposite of the derivative, which we often call the integral. Meaning, if I have a function that describes acceleration, I should be able to get to velocity if I integrate the acceleration with respect to time. Now, in terms of the constant of integration, our constant of integration ends up being the initial value of the velocity. So meaning the velocity at time initial, which time initial is often 0 seconds. We just need to know what that initial velocity happens to be in order to complete our equation. Similarly, since velocity is the derivative of the position with respect to time, if we have an equation for velocity, we should be able to integrate to get to position. The position of an object can be found from the velocity function by integrating that velocity with respect to time. And there will be a constant of integration, and that constant of integration represents the initial value of the position in this case. So this is the position at time initial. You don't need to memorize these equations. They're in the test notes. As a reminder, our test notes from this semester, these calculus relationships are in chapter 2. We see these calculus relationships right here. Velocity and acceleration. The velocity is defined as, I don't know if you've seen that 3-bar equal sign. That means not only is it equal to, it is also defined as. Well, instantaneous is where we take the limit as delta t goes to 0. Velocity is the derivative of position with respect to time. So this is our velocity equation. Next to it, we show that we can find the function describing the position, some sort of final position, by integrating the velocity function with respect to time, and our constant of integration is just shown before the integral, that initial position. Similarly, acceleration is defined as the limit as delta t goes to 0, delta v over delta t. Here's our dv dt, which happens to also be the second derivative of position with respect to time. Next to that, we are seeing that we can get to a final velocity by integrating the acceleration with respect to time, and our constant of integration is that initial velocity. Anytime we have a problem that gives us a function, whether that function represents position, velocity, or acceleration, if we're given a function, we will most likely need to use one of these relationships. If we have acceleration, we can integrate to get to velocity. If we have velocity, we can integrate to get to position. If we have position, we can take the derivative to get to velocity. If we have velocity, we can take the derivative to get to acceleration. One other thing that we're going to talk about is it turns out we'll be looking at a number of problems where the acceleration is constant. So it's a number. It's not changing. For very common examples, that of gravity, the acceleration due to gravity. Because it is equal to 9.8 meters per second squared anywhere near the Earth, it does change at that second decimal place. But that's not significant enough, so we just assume it to be constant at 9.8. That is a situation that the acceleration will be constant. So I want to talk about these equations for just a minute. Coming back to this whiteboard, using these relationships, let's talk about constant acceleration for just a second. This acceleration, we are still assuming linear motion, meaning our object is moving in a straight line. It's either moving horizontally, somehow right or left. It could be moving vertically, up or down. It could be moving along a slope or incline. The requirement is that it is moving in a straight line. In a situation like this, we say that the acceleration has a magnitude of a that is a constant. It can be positive or minus, of course, meaning if we have horizontal motion, it points to the right for positive, points to the left for negative. So we're just saying that it is a number. That's what we mean by a constant. It is not changing with time. That's what we mean. Well, coming back to our relationship up here for velocity, we can say the velocity at some final moment in time, this is still going to be a vector, meaning a direction associated with it, but we don't typically draw the half arrow above it. When you go back to the test notes, you'll see that it doesn't have the half arrow. So I'm going to go ahead and just leave that part off. But I know up here I can calculate or get to a velocity function if I integrate the acceleration with respect to time and add an initial velocity. In the test notes, they've just written this in the opposite order. The order of addition doesn't matter. So initial velocity plus the integral of our acceleration, which I'm just going to call this A, with respect to time. So again, remember dt just means we're saying t, or time, is our variable. That means the lower limit is some sort of initial moment in time. T final is some final moment in time. For simplicity's sake, I'm going to go ahead and say t initial is 0, and t final is just t, meaning however much time has passed that we're talking about, so that we can end up with an equation with t in it, and that t just represents how much time has passed. So v initial still means the initial velocity, so we would have to put in plus or minus to account for direction. It's however fast and direction the object is traveling in initially. That's going to be specific to the problem. Plus, well, if a is a constant, when we integrate a constant, we simply get the constant times the variable. When we put in our limits of t initial being 0 and t final being t, this equation ends up looking like this. The final velocity of an object that's moving with a constant velocity will depend on its initial velocity, the acceleration it is experiencing, and how long the object has been in motion. This is the equation that is describing the velocity of an object moving with a constant acceleration. We can put any moment in time in that we want. If we want to know the velocity after 40 seconds, we put in 40 seconds. This is a really nice relationship. We have to keep in mind, though, the acceleration. We've derived this assuming constant acceleration. If we are solving a problem and we know the acceleration is constant, we can totally use this equation. We do not need to integrate again. We can, but we don't need to, which is very nice. Now, similarly, if we have an equation, which we do now, of velocity as a function of time, we can integrate to find the position. So as we wrote before, if we integrate velocity as a function of time and then add that constant of integration, we find a final position. So again, dt means we're integrating with t as our variable. That's what's changing. I'm going to go ahead and integrate from t initial of 0 to t final of t again. S initial just represents the initial position. That's something unique to the problem, so that's something you will need to think about in each problem you are solving. The function we're integrating is what we just came up with for the velocity. V initial for any given problem is going to be a constant. Any one problem has one set initial condition. So it will have a specific initial velocity, a specific initial position. A, remember, we're talking about constant acceleration. So when we go to integrate this, we of course still have that constant of integration. The integral of v initial, I don't know if you remember, we can write this as the integral of v initial dt from 0 to t plus the integral of at dt from 0 to t. So I'm doing the first integral. V initial is a constant in any given problem. So when I integrate that, I'm going to get v initial times time. I'm also skipping the step, or skipping to the step, I should say, of plugging in my limits of integration. The next portion here, we have a time in here. So when we integrate that, that's the variable, we're going to get t squared over 2. But we still also have a in there that's a constant. So we get a times t squared over 2. We see this equation written this way. This equation describes the position, the final position after however much time t has passed. It describes where the object will be at any moment in time. Again, this can be used as long as we know in our problem that the acceleration will be constant, which is fantastic. It gives us a nice set equation that we do not need to derive again. We could totally integrate to get here. But if we are solving a problem and we already know the acceleration to be constant, we can totally use this equation. Looking at the test notes again, the first equation we just derived is right here. V final is equal to V initial plus acceleration times time. They leave this as a delta t. I don't tend to write it as the delta. I'm going to assume my initial time is 0, and so I leave it as t. Part of the reason I do that is simply to minimize the symbols in my equation. It just looks a little cleaner, in my opinion anyway. The second equation we just derived is right here, but again, instead of delta t, I write t, because I'm assuming our time is, initial is 0, and t final is however much time has passed. This third equation comes from combining these two first equations together. I will explain that. You do not, again, this is something we're not going to have to derive. We can use that third equation. But as a reminder, it's going to be very common throughout the semester to end up with a system of equations. Right now, we have one equation that represents velocity. Our second equation is the one that represents position. They both have a v initial in them. They both have a time in them. They both have a in them. But they do not both have v final or positions. So what has been done is that first equation is solved for time. You can totally take intermediate steps. I'm going to just jump to the solution. So we call this a symbolic equation. I'm doing the algebra symbolically. What we do is we just take this v final minus v initial over a and plug it in for t. I'm not going to go through the algebra. If you really want me to, please reach out in Canvas and I will do it for you. But when they plug that in for time and do all the algebra, it gets the variable of time out of the equation, and we can simplify it to make it look like this. The final velocity squared will equal the initial velocity squared plus 2 times the acceleration times S final minus S initial. Remember, final minus initial can be written as delta S. Going back to the test notes, we see the delta S in here. So that's what we mean by S final minus S initial. Because we have this 1, 2, 3 beautiful equations, these equations are referred to sometimes as the kinematic equations. Kine is the prefix for meaning motion, so this essentially means equations of motion. In the test notes, they're also labeled as the big three. Hopefully that makes sense now. 1, 2, 3, 3 awesome equations that relate position, velocity, and time together in different ways that can be used in any equation in any problem where the acceleration is constant. Please keep that in mind. The acceleration must be constant. So that is something we need to recognize in a problem before we use these equations. So I'm going to do a few more videos that show some samples of when to choose the calculus relationships versus being able to use the kinematic equations. I'll explain how to do that and how to choose. I will also do some examples of how to approach problems using the kinematic equations, because the approach will be very similar in every type of problem. So we want to focus on a consistent approach that will help us solve any problem that we might see. So check those out if you want to see the examples.